You are a physics professor. One would say you've been a physicist for
40,
okay.
40 years.
Yeah, that's a good amount of time. So we want to dig into explaining things clearly, the issues that it downstream effects that it can have in science if you're not speaking clearly and defining things. Is there a particular example you can use in science?
Yes. When you think about what is physics, we use the term, people know the term, but I'm not sure they really understand what we're trying to do in physics. And it'll lead to all these things with conceptual physics that you're interested in. But we first have to get that down. What is it we're trying to do? And physicists are trying to describe nature. We're not trying to explain nature. If you look at the definitions of the words, describe means to represent with. So all of physics is represented generally in the language of mathematics. That's what we do. And it's a description. If you look at explanation, that means to give the reason for. And so I start talking about gravity. People like to use the term gravity. And I say, well, just saying the word gravity is not an explanation for why something falls. Why does mass attract mass? The answer is, and I think Newton, Einstein would have answered it this way, I have no idea why mass attracts mass. That's not what we try to do. We try to come up with a formulation, usually mathematical, such that the description yields reproducible and predictable results. We can predict an experiment, the result of an experiment, before we do it. And that's what makes it so powerful. As far as explanation, if you were going to give like a proof of physics, you would have to show that it works for an infinite number of different situations. So we can't prove physics. We can't. Physics is not about, this is going to really sound bad, physics is not about truth. It's not. In fact, I think that's harmful if you say it that way. It's a search for truth. It's not really the search for truth at all. In fact, a lot of things that I teach in conceptual physics classes is not true at all. Take the most important equation we have in conceptual physics, F equals ma. That's not true. It's a great description.
Descriptor.
But Einstein found out that wasn't the absolute correct description, or the most, I should say, complete description.
Right.
He had to adjust it a little bit. He created some new mathematics to adjust F equals ma to make it work for all situations. But I teach just regular F equals ma because for most situations, it yields the right results. And so I try to convince students that, okay, there's no pressure to explain everything here. Just learn the description. Know your definitions of words. And that's the worst thing for them. It's the starting point of everything we do in physics comes from some definition. And if students accept the definition, it's a definition. It's what's going to help us, a word to describe. And if they did that, it's amazing how well they do. But if they start off with not accepting definitions, then they just can't go forward with it.
I think that's what's so great about conceptual physics to begin with is it's a way to get people into, excited about, and able to understand these super complicated things because you don't need to worry about the nuances of the super complex mathematical equations. Just get the concepts down, right? You know, and I love it. I love everything about it. I do understand with, let's say, take journalists, for example, of how and why they can get themselves in trouble along with, say, a physicist or a doctor. They're trying to maybe explain, I'll use an example, drinking a glass of wine can cure cancer, right? No, it can't. I wish it could. It can't, right? Right? Not that I know of, But I guarantee you there wasn't a doctor that actually said that. It was a journalist's version of trying to take something that they don't have a PhD. They're trying to not only dumb it down for the public, but they also don't fully understand it. all they're doing is sharing the one little bit that they pulled from a big conversation they didn't understand and almost harmlessly passed it on, but it's wildly inaccurate, right? Isn't I think
Yes.
that's kind of fascinating. So for you as a professor, you know, leading the charge and getting other people involved in physics, and I'm sure that there have been more than a handful of your students that went on to have a long career in physics. It's important that you get it right. And the luxury of that is, well, you just said you're not trying to prove anything. You're trying to describe things.
Yeah.
And that's just such an elegant way of looking at it.
Yeah, as far as just a great example, the journalism. Uh, they should have, journalists should really have some science training to it and hopefully kind of get the gist of it.
Oh, yeah.
I think of a great anecdote for that. Happened many years ago where a news show, they came on and talked about this farmer who claimed to have this new thing that would increase gas mileage enormously.
Oh, boy.
He had an old Ford, and all that he would do is put a fan connected directly to the drive shaft of the car. And he said the wind would rotate the fan, which is connected to the drive shaft, and you wouldn't need gas to run the car. And immediately, I'm thinking, well, hold it a minute. The power to overcome the drag is going to be greater than the energy he gets from
Yes.
that. I mean, but what bothered me was the journalism part. They should have never had that on the show. They should have been able to say, listen, you know, you can claim whatever you want to claim, but let's have some evidence
Yes.
that this actually has not only evidence that it works, but there's a mechanism. And the physics really is the mechanism. It's saying, okay, this is why we're able to get better gas mileage, you know, and it can't defy fundamental things in physics,
No.
or we're wasting our time. In fact, Einstein was a patent clerk for years, and he was able to look at things and say, listen, this is impossible, declined, you know, or denied, or,
Yeah.
you know, it was probably very easy for him to go through patents because he knew the fundamentals. And so I think you mentioned something about, for instance, like energy. We describe nature in terms of energy because it's really convenient. And it's something that's called a scalar. It's not even, we don't even have to worry about direction. In other words, if you talk about the kinetic energy of something, we don't care which way it's going. It's got a certain amount of energy. But this is the thing that I would say most people have never even thought about. And I have my conceptual students think about it, is that all the equations are written so energy is conserved. So anytime we come up with a new form of energy, E equals mc squared, Einstein came up with that equation so that the total energy is conserved. In this case now it's mass
I see.
energy.
Yes.
That's conserved. But it's the total that's conserved. And it's like people are constantly saying, well, maybe we just haven't figured out a way to violate energy conservation. And I'm like, well, if anybody comes up with a new form of energy, I'm going to write the equation for it so it's the same.
Yeah.
We can't be wrong in doing that. It's just a wonderful way to describe things. And it's not like we're cheating nature or anything.
Yeah.
So anyway, those are the kind of things, those fundamental things in conceptual physics. And you're right, not to emphasize little. We got to use some math, but it's real low-level math, and just trying to get down things like limitations. I mentioned words. Can't. Do people really understand what the word can't means? Can't means not doable. It's not doable. And in America, what I find a lot of students, they think of that word as being, we haven't figured out a way yet. And that really causes problems in conceptual physics. That's the fundamental stuff that they don't get the idea that, oh, you just haven't figured out a way. Science hasn't figured out a way. Well, there are things that can't be done. I wish they could, but they can't. And so, especially if you define them so they can't, like
I
energy
see.
conservation. I mean, they can't. And so I try to bring up instances where I try to convince them, there are things that can't be done. And I'll give them maybe a puzzle or something. And then I can start talking about, let's say, the second law of thermodynamics, or like the double slit experiment you mentioned.
Yeah. If you're listening still in this episode, you probably will have an understanding of, at least you've heard what the double slit is. Can I just get into it real quick?
Sure.
And then I'm dying to hear some stuff from you on that. So double slit experiment is basically, think of it as a laser shooting photons through a screen or a board with two slits in it. Behind it is another wall or a screen to capture or to, in essence, read where the protons are coming, the photons go through. And it works for atoms and stuff too, which I didn't know that until years ago. What's interesting about it is, even though it can act like a particle and a wave, so if you bombard this thing with it, on the back, you don't just see two slits, you see a series of slits, and it's because the waves are going through the slits and the strong crowns of the waves are leaving all the marks. Okay. The crazy thing about it, why it's the holy grail, in my opinion, of conversations, quantum mechanics, is all that's fine and good until you look at it or observe it. If you put a camera on it, it all of a sudden does not. It chooses one to go through. But the trippiest part of all is, even if you are only firing one photon at a time, that's where you can quickly start having these insane, run off imagination thought experiments. That's my understanding of it, at least. I don't know if I got that exactly right, but can you explain a little bit more of that? And is that something that even comes up at your stage of teaching, or are they well beyond that?
Absolutely, it comes up. And it's back to this fundamental idea that we're trying to create a description that yields reproducible and predictable results. And basically what happened was the wave couldn't do it. We couldn't get the right description in that particular experiment. It just wouldn't work out. And so they had to go to a different description. And so what we have to remember is, in physics, and I don't know if you've considered this or not, what we have to do is we got to stop thinking about what is. We got to stop with these analogies, because as soon as I say, well, the photon is a particle, and so light is made up of photons. Well, I have no idea what light is made of. It acts like photons sometimes.
Right.
Other times it acts like waves. And that's all we need. But I'm not going to say what it is. I say, if we treat it like a wave, I can get the right answers to that experiment. If I treat it as a photon in these other situations, I can get a good prediction, reproducible test, things like that. When you start talking about some of the things like, the double slit experiment or something like that, ultimately we have to create mathematics to do things that people, even Einstein, had problems with.
That's right. He did, for sure.
Yeah.
He was almost blinded by the idea of, like, no, can't be. Right. What did he say? Like, God doesn't roll the dice with, mankind. How can it possibly act one way, but then when it's being observed, acts another way? And I think that multiple people can go on multiple day-long conversations about this. And I think, to your point, you can try describing it all you want, but prove it or not prove it. To me, I had this idea, though, and it's interesting if nothing else. So if you imagine you have these double slits just getting bombarded, and you look at the back and, and it's covered with these arrays, but then when you put, you observe it, now you only have two. And what I wonder is, it's a good argument for all of this being a simulation. And I know this is going out on a limb, and I am not proposing that. I am just saying it is an argument for it to be that this is a simulation, because if you just think of it like a video game, if you're playing Grand Theft Auto or Call of Duty, that entire game and that map and that world isn't rendered. It's rendering as you're going and observing the next. So I'm just saying, what if it really is just a wide open, endless, seamless, endless possibilities? And what if once it's observed, it then acts a certain way because it has to act that way because it's now being called upon to get rendered instead of just having infinite possibilities. And then furthermore, I wonder if you and I actually even see the same end result, or do you see your version of the end result and I see my version? How are you ever going to compare? You can't, because like my brain is seeing it and it's like trying to describe the color yellow or something.
Right,
You can't,
right. Yeah.
right? What do you think of that? I know it's wild, but that's half the fun in this.
Yeah. It's with the double slit. I don't have any problem with saying, you know what, simulation or not, whatever. I don't know. I don't,
Right.
Because I know when I just have one slit open, you get a certain pattern. When you have two slits open, you have a different pattern from that. The double slit versus a single slit, they have different patterns. And so people who think like a simulation, you're just probing, like throwing a photon here and then throwing a photon there and throwing a photon. How can you possibly describe that, doing that? And the answer is, well, we don't think we can.
Right.
In that case, we're going to have to treat it as a wave that's interfering with itself. So as far as a simulation, it's a very complex simulation. But
Yeah.
how could we sit here and argue that, like the world is like just an incredible simulation of something? And there's the famous mathematician said, you cannot describe all the laws governing a system unless you remove yourself from the system. And of course, we can't remove ourselves from
Right.
the universe. So it's like we couldn't even, there's no way we could tell it was a simulation if we're in the simulation.
Sure.
You can't, you don't know.
You can't see the label from inside the jar.
Right.
Like,
That's right. That's a great analogy. It's just, and I think physicists are the worst when it comes down to saying, I don't know. For them, that's, you're just getting off on a whim. They just dismiss it. And it's a very legitimate, like philosophical viewpoint.
Sure.
It is. But I think most physicists, especially theoretical research physicists, maybe an experimentalist might be a little bit more interested, but theoretical, they're just going to
not having it.
rush.
I do think it's cool that science does seem to be becoming and maintaining a certain level of popularity, even if it's just bro science like us, not like us. You are a scientist. I'm a guy that's just a regular Joe. But the idea that teenagers, even younger kids, and you mentioned it before, and some people might scoff at it, but you nailed it. By the time you're 3, you understand. You have spatial recognition. You understand depth. You understand. You can't describe it, but you understand a little bit of if there's a hoop right there and you have a ball in your hand, you can understand the exact amount of lift and arc and everything it would take. Could you describe that in equation? No. But you understand it enough to actually make it happen. Think of the computation that is going on to make this thing do that thing and get it. It's amazing.
Absolutely. How incredible the human mind is. We talk about, in fact, I just was talking to a friend who's in the tech industry, and he's talking about AI and the involvement's going to be, but he still says we are so far off from doing anything compared to the human mind.
Yeah.
How the calculations that we do. And one of the biggest problems I have with students is they can't accept the connection between what I'm trying to say, the description that I'm presenting, and their experience. And that's always been a troublesome thing for me.
How do you mean?
Like when you talk about someone who understands the concept of acceleration, and they do very young.
Sure.
They get the speeding up. They don't use those terms, but they get it. And then when I go ahead and just put a simple equation on the board, a lot of them just don't see the connection.
Oh,
They
I
just
got
don't.
you.
They don't see the connection. And I do it every time I have to go through these, and I have them do it in class. I'm a big believer that I wish I had this kind of power, but people don't understand just because I say it. They have to go through the thinking themselves. So a lot of my classes, they're doing stuff. I will present something, and then I'm going around, and I'm seeing if they're getting it. And if they don't get it, well, then we're going to have to
Dig into
work
it.
on it until they get it.
Interesting.
Because we can't move on then. We've got to. There's got to be a certain sort of progress procedure before we can move on to more complex things like
Yes.
double slit experiments and stuff like that. So it's very conceptual physics is very basic, and students, the biggest problem they have is they think it's going to be more than that, but they already have it.
Oh,
They just
interesting.
don't see the connection between what I'm saying is the description of it and what they know already. It's very troublesome, and I kind of believe that as we get older, it's tougher for us. We may know more, we understand more about nature, but it's tougher for us than to go and describe it. So I'm a big believer. Physics should be the first one, the first science class that they take. You know, they talk
Yeah.
about biology, chemistry, physical science, and stuff. I would say, and there's been a big push to do that. Ninth grade, no, it's not going to be physical science. It's going to be just physics because you just get the fundamental sorts of things that they can relate to.
Oh,
And if we wait even 3 years, they lose a little bit of that, thinking they can relate to it. Or
Oh, interesting. And that's a great point because I got to tell you, I don't remember a ton of my freshman year of high school, but I remember taking biology, and boy, it was not for me. And I would say it squashed my interest in almost in science in total. And I'm not being dramatic here, but when I was younger, boy, I loved outer space stuff as a kid, learning about planets and stuff, and then understanding the distance between these things, understanding I didn't even understand it. You know what I mean? Like you can't conceptual, you can ideate what 100 million miles is, but we don't actually know. You know, we don't have I don't think the ability to kind of assume what that looks like. But then biology, boy, that just crushed me. I'll tell you, if as a 14, 15-year-old kid, if I was getting put into physics with, oh my goodness, it's fun. It's a lot of fun, especially, the conceptual stuff where don't figure out the technical stuff later.
absolutely,
Yeah.
it's funny you say that because I had the same experience. Biology was first, and it just turned me off. It was too observational. You just wrote down what you observed.
Yeah.
It's almost like, what do you even need my brain? Just take a picture of it and put it in a file someplace.
Yes.
That's how I felt about it.
Yes.
And then when physics came around, it was like, oh, I've got to think through a process, and it just so much more stimulating than that. And chemistry is, it's kind of, to me, I consider it as kind of a subset of physics. It's really all about electrostatics, bonding, things like that is one aspect of physics. So that's why I think physics first.
Yeah.
And that's the name of this whole push. It's called Physics First.
Oh, interesting.
Yeah,
It's funny to think about that there has to be a push for it, and that there's a machine behind this. Big biology is blocking physics from taking in the lead.
It was Leon Letterman from Chicago. He's the one who originated the idea of, okay,
is that right?
Just push everything aside. Let's get physics in first. Leon Letterman, the Nobel Prize winner in physics.
I did not know that.
Yeah.
Oh, well, he just went up a notch or two in my book. I have some interesting things to dig into, and one of them is basically the transfer of energy. And I say transfer because, correct me if I'm wrong, you can't create or destroy energy. You're just kind of moving it around, right? And something to think about if you're listening to this while you're driving your car or you're riding a bike or you're going for a walk or whatever it might be, is the energy that is being used to run your systems. You're burning calories. Your brain is expensive when it comes to caloric intake. The more you're doing, the more you're burning. that those calories are getting burned from food that you ate. The food that you ate came from energy that was stored into a seed that turned into a plant that came from photosynthesis. On and on it goes. And the fun part for me to think about, and I'm curious for your thoughts on this, is examples like, a car. You say you're in a truck and you're doing 100 miles an hour. The energy that's getting used in the form of burning fuel, the pistons are going, your transmission's spinning, it's force, it's going against the forces of, friction in the air, friction on the tires, but it's moving and you have a certain quantifiable amount of energy. Your brain is thinking certain because you're going at fast speed. And then you say, okay, I'm going too fast. And you want to slow down to 50 miles an hour. Like, think about what happened in all that 50 mile an hour difference. That energy went somewhere. And like, where did it go? Well, when you hit your brakes, it transferred into friction. So that kind of dissipated as heat energy. The tires dug into the pavement just a little bit more, which then transferred. The shocks in your springs moved. Like, is that a fair way of looking at it?
Yeah. And it is. It's just all these transformations. And what physics does is describes all the different forms of energy. But we describe it in such a way that the total is conserved. So as you mentioned, you started off with the idea of the conservation of it. It just goes from one form to the next. Physics simply came up with the equations to describe it. Kinetic energy, like you said, is 1/2 mv squared. All right? That's the best description. As it turns out, Einstein later said, that doesn't work for all cases.
Okay.
So he created a new equation. And I don't even teach it, because it's only for cases where you get close to the speed of light. So when you start talking about the energy transformations, that whole process, we figured we had it pretty taken care of. Everything was taken care of. 1905, he comes up with this universal kinetic energy, which isn't 1/2 mv squared, a little bit more complex. And we thought we had it until we started having problems with certain types of energy transformations never occurred. They just wouldn't occur. And of course, physicists are like, well, why wouldn't they occur? For instance, a boulder rolls down a hill, and just like you were just describing, it starts with gravitational potential energy, goes down to kinetic energy, and then it hits something and it stops. Where'd all the energy go? And of course, you were right. It goes into, sound, carries away some of the energy. Of course, the heat, some vibrations and stuff like that. But why can't we just heat up a boulder and have it roll back up the hill?
Right.
Because why wouldn't energy be conserved? I give it a certain amount of energy, lots of thermal energy. Why doesn't it go back up the hill then? And of course, everybody, a 3-year-old would know that's not going to happen. They already understand. No, it doesn't work that way.
Right.
And so then physicists had this whole new problem. And of course, that led us to thermodynamics and the idea of entropy. So a lot of people like to think of energy as kind of a subset of this whole idea of entropy, that the transformations only go certain ways. Kinetic to potential, yes, but not 100%.
Right.
Yet some of it's going to have to go to other forms. So you can't have a perfect transformation in certain ways. And so this whole idea of the second law of thermodynamics, oh my gosh, that conceptually, that throws people. I mean, it did me.
It certainly throws me. And I think I'm not 100% sure what you're referring to, but I think I follow. I know that when you speak of entropy, most, I'm going to say, systems prefer a low level of entropy, right? So it will use energy to then make things lower entropy or chaos entropy.
Yeah.
We probably define what that means.
Right. Yeah. The word chaos is a good disorder. Chaos.
Yeah. So things that are in a lower form of entropy, everything's nice.
Yeah.
That's why you can remember the past and you can't remember the future, because the future is too much entropy, where the past is very low level. It happened.
Yeah.
Right.
Yeah.
But you could argue, well, the future happened already too. We just didn't witness it yet. There's it's so fun to just think about all that stuff. There's just too much entropy out there to try to organized into a neat packet to then describe the future.
Yeah. Or if we do, it's going to take an enormous amount of energy to create that sort of organization. It just takes energy to then reorganize something.
Yeah.
And so there's no free way out. But people, including religious people, would say, well, you can't explain why it doesn't do this. And so we had to create this to describe under which circumstances it does this and under which circumstances it does something else.
Yes.
And that description seems to be good. We have not found any evidence that's contrary to it. Because if we had situations where we heated up a boulder and it rolled up the hill, if we had a situation like that, well, we're going to be throwing out laws.
You got some splaining to do.
That's exactly right. We're going to have to recreate. And to me, I don't see it much different than like artwork. If I was to draw a tree and someone said, that's not a very good leaf you have drawn, is that what that is? A leaf? I said, oh yeah, well, I better adjust that. I better draw a better leaf. That's really what physicists are doing. They're coming upon new things and saying, oh, that description doesn't work very well.
Oh, it's a great way of describing it. That is going to forever be ingrained in my mind. Thank you for that, because it's a great, because I know that a lot of naysayers isn't the word, maybe just people who don't want to get it, where they're like, oh, how convenient. You don't know a thing, so then you devise a formula to explain away that thing. And the answer is no. No. But also, yeah, kind of. Like, meaning the equation just didn't exist yet. Or let me rephrase that. It wasn't discovered yet. Yeah. It existed as a way to describe it. It just didn't exist to us yet. I mean, it's similar to if you reverse, you hear people say like the probability of life anywhere else is, astronomically small, and, everything evolved for us. And people are narcissistic. I think it's insane to think that the entirety of the universe created for little old you and me. I think it's more likely we're here because of those things. Those things aren't here because we needed to be here. No, we're a byproduct of all of these things falling in place. That's my...
And I agree with that.
Yeah.
You already mentioned why perhaps we haven't come in contact. You mentioned it. The unbelievable distances.
Oh my goodness. Yeah.
And we just have not been around long enough for anybody to even be interested in,
Yeah. We can just take 10 seconds to quickly get that soapbox out of the way, where radio is the longest, fastest thing that we've had going. Even let's just be generous and say we've had 150 years of...
That's generous.
That is not even... We didn't even make it to any sort of other visible. We're hundreds of millions of years away from the next, galaxy, let alone the globular clusters. Are you kidding me? And then, oh, by the way, if and when they do receive it, you think they're just going to say hi back? It's going to now come back and take just as long.
Yeah.
Like, come on. So anyway, I do believe now that it's fun to be steeped in the world of science, because hard pressed, I would say it's going to be impossible to have any sort of serious scientist at any level to say that it is factual that we are alone in the universe. You're almost going to hear the opposite, where it's pretty much mathematically impossible that we're the only things that exist.
Right. I hope.
I would hope so too. Yeah. They're not going to look and sound like us and wear cologne and drink coffee, but you never know. They might. With that transfer of energy, the reason why I like it so much, and when I say it, I mean that topic, is, hear me out here, because I'm what we define as alive, and I have hopefully a healthy brain. I can think about this time next year. What do I want to be doing in the 1-year anniversary of today? Mm-hmm. And I can sit here and I can draw out, which is using energy, transferring it from thought to mechanical, having the ball of the pen roll to the ink placement on the paper, to then another form of energy, which is going to swipe my credit card at Home Depot to buy the material because I want a new table for this time next year. I can then turn the table saw on, use my screw gun, get the wood glue out, and make a new table for the 1 year anniversary of that show. Couldn't you say that that was just a transfer of energy, which was my thought, into a real tangible object?
Yeah, so it's like you're talking about the thought itself
Yes.
being like a form of energy.
Yes.
Because you're right. You clearly used energy to create the thought. So where'd it go? Into like a thought. And I would definitely say physicists have not described the nature of that energy. And what I mean by that is they haven't gotten a formula for it. Now, this is what I claim most physicists would probably say. They would say that, yes, the thought is a unique set of like waves that you have created. We have detected brain waves. So really, we've got things, electronic equipment that can detect a brain wave, and your thought is unique. It must have some sort of combination of some sort of electromagnetic waves. I mean, literally electrons. There's an electrical circuit in your brain that's creating these electromagnetic waves, and I would say those carry the energy out. And of course, it's not perfect transfer of energy either. I'm going to guess that it's extremely small percentage of the energy given off to give that thought. But if that thought, to me, is floating out away from you, it's being sent out, it's literally occupying space. But I would say that it would be described as an electromagnetic wave. The thought is a unique combination of waves that it carries energy, electromagnetic energy. And I'm going to guess it's not a lot, but it's definitely measurable.
Sure.
So the question is, does it stay in space? So I have a thought. I think this is kind of what you're maybe getting to. If I had a thought about doing something, and now it's produced these waves, and then I say, forget about that, and then I go do something else. The question is it somehow occupying space yet? And I would have to say yes.
Yeah.
But it is occupying space that is like moving.
Right.
It's moving away from you.
In all directions.
Right.
Yeah.
Right. And so, yeah, it's a great idea. I mean, but physicists, that's what they do. But I would claim most physicists would say that. They say, we would describe that as an electromagnetic thing. But is it a series of photons?
Right.
And I would say, I have no idea. Whatever works, if you have a wave go into an operational amplifier and then you can somehow record that wave pattern that you created by thinking a certain thought.
Yeah.
If you can record that. And I think that's there are technologists trying to do that. This whole idea of singularity, being able to record your essence, your emotions, your consciousness, and then put it in a computer, and then later have that computer on board a robot, to recreate you.
Yeah.
I don't know if you think that's possible.
I do think a form of that is possible. I don't think it's as clean and cut and dry, to your point, where you're going to have some leakage, for lack of a better term, right? Where I do think if you think about how powerful, either on a small scale or a large scale, a thought could be, even if 1% escapes into the ether, your thought that is, and the rest went into, like, you said heat and all the other things. Well, what if that 1 or 10% is so much more powerful than we could ever dream of, that's all it needs. That's all it takes. And the heat that's going off is just the byproduct, again, of allowing that thought to go out there. I mean, I love the idea of it, and I so want it to be true, but I don't care if it is or isn't ever something that is quote unquote true. To me, I just believe it. And I use it and I practice it, making things manifest based on your thought. And if you have a clear intention, clear intention and you want a new car, say, you have the thought over and over again of feel the leather of the steering wheel in your hand, shift the gears, press the clutch, smell the exhaust, clean the seats with the leather wipes. If you do that enough, and if you synchronize as much as you can that's happening, in your mind to that one particular thing, and you put it out there, I don't know. I gotta say, it kind of seems a little bit true, because where I am now versus when I was, say only 10 to 15 years ago is mind numbing 180, and all for the good. And it was because this concept was thrown out to me that for some reason, that's how I interpreted it, where I was like, that is interesting. And I've never been able to shake that feeling. So the transfer of energy for me, I'm allowing myself to believe we all have unbelievable capabilities. Just guard at how important it is and how important your thoughts are, both positive and negative. And I think there's something there.
I think you've really hit upon just the whole idea of Eastern thought. Like you said, it's not like you have to sit around and try to explain it or anything like that. And the whole idea of Eastern thought, different than the Western thought, is that you're one within the target. It's to hit, to pull a bow back, and shoot an arrow into the bullseye from 50 yards. If you're going to do that mathematically and using physics and stuff like that, it's probably not going to happen.
I mean, maybe in a vacuum, but you start adding in wind and other factors, it probably, hey, I hate to say can't, but not going to happen.
No, it's not. But yet you can get a person in those situations.
And do it.
And there's unbelievable amount of, I guess I would call it more awareness of, in concept of nature. You're just, like you said, the feel of the leather, or, all that stuff is going through your human mind. It's not just one little thing, I got to keep it at 55. Yeah. There's all sorts of, I tell Barb, my wife, I say, I don't want to just know the fastest way to get someplace or the shortest way to get someplace. GPS gives me those two options. I want to know what the safest way to get me, and think how much would have to go in to AI to give you the safest way. It would have to take in so much information, but a human being does that. They could look at something and say, "Nah, I don't want to go that way. This does not look good." I think there's going to be a lot of backup there that may or may not be, but it
knows it's on a curve. It knows that it doesn't get the sun during the day, so the ice probably didn't melt. All those things that we're able to forecast. That's a cool way of thinking of it. Yeah.
But that's you're talking about something that is just the energy transformations of developing thought, and then the stimulus of so many things, and how you can just take it all in, and the mind can deal with it all. Where a computer, it's going to be, that's what my friend was saying, to get a computer to be able to do that, it's going to be another league. You're going to have to go, a long time, if ever, that we have that to be able to duplicate something that's already at its max capability.
Right.
I don't think people necessarily use that capability all the time.
I would venture to say you're 100% correct there. Yeah, unfortunately. What's a part of physics that you hold near and dear that you kind of just gush over?
My favorite is one that I think would help students accept what physics does, and that's gravity. Especially things like the general theory of relativity, just how eloquent it is, and the incredible insight that Einstein had. And we're talking conceptual, intuitive sort of thing, not mathematical. He used his wife to do a lot of the mathematics. His wife was a PhD mathematician.
He was the thought experiment guy.
Yes, that's exactly right. He thought about thought experiments, and he wasn't always right. He was wrong about a lot of things, but general relativity, how it was so far ahead of its time, that's what I think I'm just really excited about. The idea that someone could come up with a description that we may not even use. It wasn't even really used for 80 years. It was shown to be correct. It yielded the correct experimental results about 12 years after he published his paper.
Oh, okay.
That's why he didn't win a Nobel Prize for that, because they couldn't test it yet. They had no way to test it. But it was about 12 years. But now we use it. I mean, if we don't have the general theory of relativity, we don't have GPS, which is it's absolutely a wonderful thing. The idea that I got here today partly because of Einstein.
Yeah.
That he, helped.
It's remarkable.
Yeah.
And the understanding of silicones, because that's in every computer ever. We should actually take a second to just let you describe, if it's not too much to ask, relativity and what Einstein actually meant and why it's so profoundly important.
Yeah. With special relativity, 1905 is when he published it. His thought experiment was, what would the universe look like if I was traveling in a wave of light? And from that, he saw how space and time was in a very simple. I go through it with conceptual students. I can talk about the thought experiment. And the mathematics is only algebra. Mm-hmm. So it's not hard mathematically to show his special theory of relativity. And we didn't have direct proof of that. We had some indirect experiments, but not direct. But it was 1967 or 63. We developed the atomic clock, and then we put atomic clocks on a plane. This is an actual experiment that occurred on a plane, kept a couple at the airport, all synchronized, and he flew it around the world. And then they flew it around the world the other way to compensate for the Earth's rotation. And we got the difference between the clocks. And it was exactly what Einstein predicted 8 years after he died. Yeah. Now, that's good science.
That is good
science. You got a
science.
great description of nature. He didn't even know. And by the way, he didn't win the Nobel Prize for that either. He won it for a completely different effect. They couldn't prove or get evidence of his theory of relativity until years later, even after he died. And so what it is if you're moving, space and time are not the same. So if I'm moving, how time moves forward, it always moves forward. How time moves forward is not the same as how time moves forward for you. We may think we're fine, everything's normal, but there's a difference between us. And that's what he, purported.
So the most famous example is probably the train. You're on a train doing 50 miles an hour and you throw a baseball to your buddy at the other side of the car at 30 miles an hour. The viewer standing outside sees the train go by. That ball is doing, 80 miles an hour, the 50 plus a 30, or at least looking like extremely fast. But from inside that car, it's only going as fast as you threw that ball, right? It's kind of easy to understand, but at the same time, is it like if you really turn off all the other white noise and you start thinking about the implications of what that means, you can start understanding time dilation. The faster you get to that speed of light, like things are slowing down quick. When you get, close, quote unquote, to a black hole, those things are going to slow down. The twins, the experiment, where one was in space and came back and, didn't age quite the same as one. Like, that is incredible.
And it's funny because he aged normally. Everybody aged normally. They just don't age at the same rate because they're in different time frames. But your example with the train, that's exactly the one he was thinking about. Two events, the time between two events, throwing a ball to somebody. And then he said, well, what if I threw a wave of light to somebody? What would happen then? And that was it. That led him in simple mathematics to this whole revelation.
Off you go.
And why in 1905, why couldn't they have done that earlier?
Yeah.
But it was just time to have a human being who did that.
Yep.
And the general theory is similar, only he deals with accelerating frames and then you can involve gravity because gravity accelerates things. And so now, the clock doesn't work at the same rate, let's say in space, than it does on the planet's surface. The ones on the planet's surface, they just do not tick forward as fast as the one. And Einstein predicted the exact discrepancy between the two. That's what his laws do, his theories, and a little bit more complex mathematics for that one. But that's what you're referring to. So if you get to something very gravitationally strong, a black hole, you can actually stop. So a person observing it from the outside is saying, your clock stopped. And of course, the person there would say,
What are you talking about?
everything's fine.
Yeah.
What do you mean?
Yeah.
And so people say, that didn't make any sense. Well, so what? It's
Sorry.
It's what happens. Nature's a weird beast.
Yes.
And that's why I always come back to gravity, because I say, well, does gravity really make any sense? Why would mass attract mass? That doesn't make any sense to me.
It does,
What's in between here?
Yeah. I mean, would you consider Newton then to be, the guy for physics? Or is there one particular leader or forefather of physics?
Well, I do ask, in fact, this Wednesday, I'll ask my class, I'll say, Newton is considered the number 2 most important, most influential person in the last 1,000 years.
Number 2.
But if you ask like 1,000 renowned scientists and political leaders and everything, Newton's number 2. Einstein's number 6. Shakespeare's 4. Of the contributions that they made. And I ask them, come in on Wednesday with the name of the number 1 person. And you know who it is?
I mean, I'm dying to know.
I think Bill Gates is on that list. Abraham Lincoln
Lincoln,
is 16 or 14. Gates is 91st. And
boy, don't tell me. I'm going to actually take a second.
Because I wouldn't necessarily, I tell them, just go look it up, because I would not expect most people to know who is considered the most important person in the last 1,000 years. We're not going back to Jesus or Muhammad, I think it should be Newton.
Yeah.
He should be number 1 because he not only described nature, but he created a whole branch of mathematics that is used so much in today's world. Calculus. He really invented calculus and took a big step. But anyway.
I hope it's not like an Alexander Graham Bell kind.
Gosh, where is he? I don't know where he's at. I think he's in the 20s.
Okay.
So
which is great, but boy, I give up.
It's Gutenberg.
Really?
Yeah. The printable typeset. Or movable typeset that we could now systematically record our knowledge. All those ideas to have a very effective way of recording knowledge. And supposedly he wasn't the first to invent it. Chinese were supposedly the first to invent the movable typeset. But we were so isolated from China. China was really kind of isolated.
Oh, yeah.
And so, anyway.
That's interesting. Yeah, I would agree with you. My limited knowledge on who that is, and I appreciate why he's so high. But yeah, Newton, I feel like, is number 1.
Yeah.
Who's deciding these numbers anyway, Dave?
Yeah.
Right? Okay, come on. Yeah.
It's kind of random.
Do you find that the age group you're teaching is more receptive, or not just the age group, but the position that you're in? I think what I'm trying to say is, when people decide they want to do something for themselves, say take your class, and they're not at like a tight, regimented campus where they have to take your class. Right. If you're in more of a lower kind of a relaxed setting, I'm assuming, I don't know. Do you find that the people then want to be there in your class more and then get that same level of excitement?
Yeah, that's what the beauty of community colleges is all about. Small classes, and it's definitely more intimate. They're there to work on getting a job. They want to they're not necessarily wanting to be in physics, but they got to have it.
Yeah.
And they know they got to get through it for a job. The traditional student, like at a university, first, they do not have world experience like a lot of the students I have. Probably the average age in my class is 28 to 30, I would say.
Okay.
Something like that. Whereas, of course, traditional students, you're talking 18 and 19-year-olds. And these people have been out in the working, blue-collar sort of jobs, and they have a better feel for nature. They've had to, work around a machine and something that rotates and something. But those same people didn't have the traditional background as like a university student, and that is more math. And so they're prepared for the concepts better, but they're less prepared for even the small amount of math. I have one student who's 30 this semester, and he got kicked out of high school. He never did finish high school, never even took algebra. He probably has great intuition. I already talked to him about it. Probably got great intuition, but he doesn't know the language.
Yeah.
And so a lot of times what happens is I end up helping them with the language, and we don't always get as much done with the concepts. And that's disappointing, but
I'm sure, but I think that's also okay. Because he might not be the guy that necessarily, like, for example, if I'm excited to hit a stage in my life when I have the bandwidth to just for my own sake, I would go take some of your classes. I think it would be fascinating. What am I going to do with it? Nothing. Nothing professionally. I'm not going to go use it to pay my bills and feed my family. It would be for me just because why not? So I wonder how I would approach that if I was a teacher and I think that would mean a lot, for me at least.
It's funny when you say that, because I do deal with a lot of blue collar working class people. And I do tell them, even if you're not going to use anything specific equation, I even tell them, you're not going to remember these equations a month after the class. I could care less. I'll give you a formula sheet. This is not about that. But I tell them, you will. If you take advantage of this class, you will use it, and it'll save you money. It could save your life. I talk about a lot of cases where people didn't understand a concept in physics, and it killed them. If you don't remember who started World War I, it's never going to kill you. But if you don't understand the idea behind stopping distance in a car,
oh, that's a great point.
You're going to die.
It could.
In an accident.
I could see how that could fall into your past experience. You were either going for or had your pilot license, correct? Yeah. So, I can't imagine how many applications this. If you don't know, it could kill you. I'm sure you have some examples of how piloting a plane that matters.
Yes, yeah. In fact, I think I use a lot from what I learned about becoming a pilot more in class than I ever learned in any physics class.
There you go.
Because it's the connection between nature and what I'm trying to teach. And yes, there's at least one incident that if I would have understood something in flying, I'd be dead right now. I wouldn't have known what to do.
What was it?
It turned out to be a thermodynamics problem with a plane. Okay. Where
there it is. I knew there was a special heart for thermodynamics with you.
Yeah. So I can tell you the story.
Please.
It's very quick.
Take your time.
It's in small aircraft, they use a venturi to create a low pressure to suck gas into the carburetor. But when you do that, when you create that low pressure, it's a Bernoulli effect. You create that low pressure, the temperature goes down, which is the ideal gas law. The temperature goes down, and it can actually freeze the water in the air, the humidity, and block the gas. It's called fuel starvation by carburetor ice, they call it. And so it can be 70 degrees out, beautiful day, and your engine will stall. It happened to me a couple of times where all of a sudden the RPM of the engine just starts dying, and you've got to recognize, I got ice on my carburetor, and you pull a thing called the carburetor heat. It's just a lever that deflects the manifold heat onto the carburetor. It just melts the ice. Anyway, so no problem. I would lose 100 feet. It would be no big deal. Well, I was teaching a class about the confluence of these ideas and how it could kill you if you don't get it. And a guy in the front row, he said to me, "That's what happened to me. That's what it was." Just then.
No.
Like 3 years earlier, he was on his first solo flight, and the engine just died.
Oh, man.
It just starved.
But he didn't know why.
No. Well, he knew, but he didn't get it.
Gotcha.
And so his instructor, I'm sure, told him about carburetor ice, but he didn't understand the idea that 70 degrees out, how can you get ice on anything at 70 degrees?
Yeah.
Anyway, so he landed in a bean field. It was in Illinois.
Wow.
A lot of flat areas to land a plane.
He lived to tell about it.
He never flew again. And the NTSB guy, when they came out to investigate, they have to, supposedly the NTSB pilot flew it out of the bean field because, of course, when it landed,
It's fine.
it melted.
What is it, NTSB?
The National Traffic Safety Board,
So if you have some sort of an incident like that, what happens?
they always,
They come out and respond.
yeah.
Is it like you're in some sort of a trouble? Is it like a no-no? Do they say, hey, congratulations, you're alive. Now here's like a fine? Like what happens?
I don't know if there's money involved, if there's fines.
It's always
but
punitive.
it depends. I mean, if you did it on purpose.
Well,
but
sure.
He immediately determined this kid didn't understand that you can get carburetor ice
Lucky
at
to
this
be alive.
temperature. And so I think in physics, there's lots of instances. If you don't get it, it could kill you. Like we lose about 35 to 40 people a year in America due to lightning strikes. And you can do something to mitigate the
Yes.
chances. You can.
Is it that many on average, really?
Yeah, it's
Yeah.
actually not. I mean, we lose 30 to 40,000 on the highways.
Right.
And I think that's because people don't get stopping distances. They think they can stop in a shorter distance than they can. And that's a biggie for us. I really push that in my classes saying, listen, if you doubled your speed, you quadruple the distance it takes to stop. Most people think you just double your distance. No, that's just not the way nature is. You quadruple. And then we show them the description. And we have several descriptions that kind of verify, yes, it's going to take you 4 times if you're going twice as fast. Anyway, with a lot of those ideas, I want to try to, I'd love to be able to say, you know what, I could be saving lives here.
Yes.
Because if they get it, they're going to, for instance, slow down.
Yeah.
Especially under certain circumstances. Speed is the killer.
Well, I'm so just fascinated that you went this route because it's a perfect segue to the last thing I wanted to talk about. It's kind of a two-parter is speed, right? In particular vehicles.
Mm-hmm.
And you're doing 80 miles an hour. You are something like 50 or 60% more likely to die than doing 60. Can you explain why? I think some of it may have to do with the inertia, the internal collisions that happens in your body after the external collision of the car. Can you talk about that a little bit? Because you started talking about it.
It's related to the last thing with stopping distance. So say from 40 miles an hour to 80 miles an hour. The energy of the same car, 40 and 80, the energy of the 80 mile an hour car is 4 times greater. It's moving twice as fast, but its energy is 4 times greater. The amount of energy goes up drastically, a lot more than people think. They think, well, I only have twice as much energy, it's going to be worse, but it's much more. And I think that's the key is you can't just think linearly. If we can teach anything in conceptual physics is things don't progress just linearly. Cause and effect aren't described just as a line. They could be parabolic or quadratic or something like that, exponential. And so I think that's a biggie. I want them to be able to look at an equation and say, okay, what if I change that a little bit? Going from 60 to 80, how does it change this? And when they see how much it changes it, maybe they can start to say, okay, maybe I should slow down.
Slow down a little bit.
80's not a good idea.
Yeah.
And I just think that sort of relationship, any relationship, if you can understand how one thing affects another, that just allows you to be more aware, cautious, because 30 to 40,000 people a year dying.
It's insane.
And I say it's one reason. They're moving too fast.
Yeah.
By the way, I did an experiment one time just to see, because we all know it happens, but just to see. I went from Springfield to St. Louis, 90 miles, and I decided I'm going to find out how many people are speeding versus how many are going slower than the speed limit. No kidding. I did this experiment. I put my speedometer or my cruise control at 70, and I knew it was accurate, plus or minus a mile an hour.
Yeah.
194 people passed me on the interstate. I passed 3.
Wow.
People are traveling too fast. There's a reason 70 is a good, we have that trade-off between getting there in time and being safe, as safe as we can. And 70, people are going to die at 70, all right? But a lot more are are going to die at 80.
A
And we've got a
lot
lot of them going
and
at
they
80.
all have cell phones in their hands while they're doing said 80
Right.
miles an hour, you know.
Which means that affects reaction time and
Sure.
stopping distance.
Yeah, because you're not giving your spotlight attention on one thing. You're splitting your bandwidth between, you know, the TikTok post you're
Right.
looking at. I mean, it's a problem, obviously, and that's for a different show.
Yeah.
But the last part, and as that two-parter that I was alluding to, is can you explain something that I don't understand? And I think that I'm not alone. If you have a vehicle doing 60 miles an hour, and then you have another vehicle doing 30 miles an hour, and they collide,
Yeah.
I think most people would say, wow, you know, that was a 90 mile an hour collision, 60 and that
Yeah,
30.
right.
In fact, that is not the case.
Yeah, good.
Help me.
Yes.
Help me, Dave.
Okay, so that's what you're referring to. I'm sorry, I segued away from that.
No, you're good. No, you did good.
Okay, so let's just take as simple of example as possible. Let's say you had two identical cars moving at each other at 60 miles an hour. They're identical in every way, and they hit head on. There's no rotating or anything. They just smush each other, all right? So if they started at, each one was going 60, what would be their ending velocity?
0.
0. Yeah, excellent. And so they basically, each car went from 60 down to 0. That's what they did.
Okay.
Not from 120 down to 0. They went from 60 down to 0. Say you take the same car now and run it into a brick wall. You're going 60 miles an hour and you run into a brick wall. All right? Head on.
Yes.
Of course, their final velocity, this brick wall is really strong.
Yes.
Their final velocity is 0 again. So they went from 60 down to 0. Which is worse? Now, I mean, more people may die in two cars, of course.
Yes.
But I'm just saying, which is worse for like a car to do? And the answer is, it's the same.
Same.
It's not the velocity, it's their change. How did that? Forces are felt by change in velocity. You don't feel that you're moving 67,000 miles an hour around the sun.
No.
But that's how fast we're moving.
We would if it stopped all of a sudden.
That's right. We'd be gone if we stopped. And so that's what, I talk about. We talk about what's before and after. And that's, like you get Earnhardt. If you remember Dale Earnhardt, Earnhardt died. It really bothered me.
It looked so benign.
That's exactly right. It looked benign. It was like, because I was thinking it was before and after. He hit the wall, glancing below on the wall. He bounced off the wall a little bit, but his speed might have gone from 190 down to 170. So I'm thinking the change in speed wasn't that much at all. So why did he die from that? And it turned out to be his change in speed in this direction,
Yes.
not his velocity going this way. He had a very quick change in speed, which of course
Broke
his
neck. Yeah.
and now they got new, things to support your neck from doing that. But people were saying, well, what do you expect when you hit a wall at 190? Well, if you hit a wall at 190, you just glance, just scrape it. Nothing's going to happen.
Not much.
No.
Yeah. Yeah, that's great. All right. So I got to say, I feel a little silly for not being able to articulate that so well in my mind, where I'm not kidding. I couldn't wrap my hand around it because I'm looking at it like, well, there's got to be inertia in play, but nope. It's just, it went to 0.
Yeah.
So it just went to 0 and
change.
Stop. Don't overthink
Right.
it. Yeah. Which is so great.
Oh my gosh. It's one of the most hardest things for people to get the difference between speed and their acceleration. It is really hard. I'm going to be fighting that in the class I'm teaching now for weeks. I'll be fighting that.
All right. Well, you're making me feel better, so I appreciate that.
It's very common.
If you had, say, let's say a ball suspended, it's probably a common experiment that's done. It's a ball suspended, a heavy, 5-pound lead ball, and it's hanging from twine. And then under it is a piece of twine. If you were to just take that and pull, which twine would break? And I know the answer. It would 100% of the time be the top string, because it's the force of you pulling plus the weight of the ball. So it's like, but the ball's not doing anything. Yes, it is. It's adding whatever it weighs to your push. But then if you took that string and yanked it real quick, the bottom one would break because of the
inertia.
inertia, right? Because inertia just wants to do what it's doing and it's staying still.
Yeah.
It's being lazy there, right? So first off, am I right in that? Let's check my math.
I mean, that is absolutely that's exactly what would happen.
Okay, yeah.
And we talk about it in terms of it's not just the force, it's how long the force is supplied. The change in momentum is dependent on the force that you apply. And so if you apply a force for a very short time, that ball's not going to undergo a change in momentum.
Right.
So if you apply that force for a long time, that ball will undergo a change in momentum
Yeah.
more than the other way. So that's the whole idea. That's how we describe it. But you're absolutely right. That's a great example of.
It's so fun. It's just a fun thing to do. You know, the concept and the idea of this show is called Notable Being because I want to have good conversations with people who have adapted, overcome, or excelled at any one particular thing, right? So it's fun for me who understands maybe, you know, this much of any given topic to talk to somebody who understands that at a greater, by far, you have a lifetime of experience and knowledge behind it, but we can still talk about a thing. I'm curious to see how deep in the weeds you can really get. We're not going to go there though, Dave. We're not going to do it.
But I do want you to know, because you kind of alluded to it, it's not an intelligence thing.
No.
It's an interest thing and an exposure thing. And so I always think of having arguments with my dad, who was a very bright man, brighter than me. He had a high IQ. And yet he would have little misconceptions about physics. And we would talk about him and stuff like that. And there were several instances where he would bring up something like that. And I would say, oh, well, you're getting the perspective of this person. So it looks like this, but it's not. And then we'd go through some, physics idea to do it. But very bright, just hadn't been exposed to it.
Right.
And once he got exposed to it,
you can't unsee it.
Right.
Yeah,
Right. That's
yeah.
exactly right. And then he can apply it to many situations like it and stuff. So no, that's how I treat the students. A lot of them, they're very intelligent people. They just never have had the proper exposure. Like you said, you've had a days of enlightenment.
Yes.
And just something exposed you to something.
Something just clicked.
Yeah.
Yeah. Yeah.
And that's what we hope.
No, that's
students
cool.
get.
I mean, it's a wonderful thing that you're doing, and I thank you for your service of helping a portion of the population use their brain and potentially use that for good. As the show is winding down, I have this thing that I do at the end of every episode where I grab this book, and in here is a series of just handwritten thoughts, questions, ideas, whatever. I just kind of flip through, and I'm just going to land, and wherever it lands, we're going to talk about it, man. So this could get wild, but I want you to, do a deep dive.
Okay.
So this is what it is. Do you gain more by asking questions and having them answered, or by discovering the unknown by mistake? So I'm going to ask that again. Do you gain more by asking questions and then having that question answered? Or do you gain more by discovering something just by stumbling upon it?
I definitely think you get more out of it when you stumble upon it. This is not quite the answer to that question, but just your own discovery. You put your energy into something, trying to figure something out. I think it's better if you do it on your own. And I know I tell students all the time, I can't learn stuff for you. I can answer your questions, but you have got to learn it. I teach, and then there's learning. And I think a lot of students somehow think, well, he talked about it in class, so I must understand it. And it's just not that way. People just don't learn really, especially concepts, just by someone telling them. So I think, definitely, if you just come upon it, on your own or by mistake or something, that's invaluable.
Yeah.
If you can that way. And the enlightenment, you don't always know how it comes in. you all of a sudden you just have this thought that's saying, why does it do that?
Yeah.
And you investigate and you find out. That's the best way.
I agree 100%. And I think it's not just because it's not as satisfying to just ask a question and have it answered. It does something to you when you stumble upon it, work at it, whatever it is. If and when it happens organically that way, for me, it is so much better. Although I will say it felt really good having you explain in 2 seconds why 2 cars doing 60 is still that felt good, man. And I was okay. I didn't stumble upon that myself, but I think it's time to end this one. But believe it or not, we've been going on for over an hour and a half.
Wow.
I think that there's going to have to be some future segments with you and me where I'd love to just tease out a little bit of the topics we talked about today and then see how deep we can dive on something before you lose me and the people tuning in. But I mean, from a fun perspective, not a challenging way, but a real fun conceptual stuff. If you are into that,
Of
I'd love
course,
to have
I'd
you
be
back.
interested.
Yeah.
Yes.
This was wonderful.
Yeah.
Thanks for sharing your
This-
time and your knowledge. I really appreciate it.
You're welcome. It's
Okay.
been an honor. I've really enjoyed it. First one that I've ever done, and it's just really neat.
Well,
It just,
man, you did really well. So thanks, Dave.
Sure, you're
Okay,
welcome.
Thanks.